Yeah, thank you very much. So I would like to thank the organizers for inviting me. And also thank you all for picking my talk with so many interesting things going on at the same time. Yeah, so I'm going to tell you about this joint work with George Lam and Yichen. So it's about G functions. And the goal is to try to understand them in the easiest non-trivial situation. And I will spend maybe half of the talk telling you a bit of what G functions are, why they are interesting, examples, open questions, these kind of things. Okay, so let's start with the definition. This was introduced in this fantastic paper by Siegel from 1929, which is called on the applications of Diophantine approximation. And there will be a conference to celebrate the 100 years birthday of this paper in a few years. And it's not the main topic of the paper, but one of the things he does is to introduce this notion of a G function. So I will first define G functions with rational coefficients. So these are power series with rational coefficients. And then we ask two conditions. The first one is that these power series are solutions of differential equations. So by this, we mean linear differential equations with polynomial coefficients, and the polynomial itself have rational coefficients. And the second is about the growth of the coefficients. And it has two parts. So the second part is of more arithmetic nature. The first part is that the absolute value of the coefficient grows at most like c to the n for some constant c. And the second part is about the common denominator. So you look at the first n or n plus 1 coefficients of your series, and you want that the common denominator also grows at most at c to the n. Okay? And then what is a G function in general? There's no reason to restrict to rational coefficients. So you could give a definition in the same spirit, but maybe a fastest way to say this is just a linear combination with algebraic coefficients of G functions like here. Okay? So this is the main object of study. This displays the beginning of the title. And then what we call the differential order is the minimal order of a differential operator that annihilates the G function. So we will be interested in those which are a solution of a differential equation of order 2. And then just some small comments about the definition. So the first one is the existence of a differential equation is equivalent to the coefficients of the power series satisfying some recurrence relation. So an plus 1, an plus mu are related by some equation where the coefficients are polynomials of n. And usually if you are given the coefficients, you first find the recurrence, and from this you construct the linear differential equation. So that was the first condition here. And the second condition has two parts. So the first part says that actually the series has positive radius of convergence. It could be a polynomial. These are trivial examples of G functions. But then this is in tension with this condition of integrality. And then this condition says that the radius will be finite unless it is a polynomial. Okay. So power series with a finite positive radius of convergence. Okay, let me give some examples. So we start with the one that motivates the name. So the explanation for G functions is the geometric series. This is Siegel's explanation, and then I will propose a more interesting explanation. So this is an example. In general, all rational functions such that 0 is not a pole. Okay, so if you remember your derivatives, this is a solution of a differential equation for the 1. It converges up to the first pole, and then you just need to invert the constant term in the denominator. Okay, so more generally, algebraic power series, you have a power series which is algebraic over rational functions. This will be a G function. The interesting part is the growth of the denominators, and it actually satisfies a stronger condition than the one in the definition. It's what is called globally bounded. So it means that up to homotopy, the thing actually has algebraic integers coefficients. Okay, this is a theorem of Einstein, but I'm not going to say much more because this will be explained in Daniel's talk later. No? No? Okay, so I'm not going to say more anymore anyway. Yeah, so it's a stronger condition. some construction you can do is you can start with a rational function in many variables given as a power series, and then form what is called the diagonal. So you take the diagonal coefficients, so A0, 0, 0, A1, 1, 1, and then you create a generating series. And then this is a G function. So the interesting part here is it's very easy to prove the growth of the coefficients. The interesting part here is this is a solution of a differential equation. And actually, this is a generalization of examples 1 and 2. So 1 is the case of one variable, and 2 is exactly the case of two variables. So diagonals of rational functions in two variables are algebraic functions, the two same sets. But in general, you get transcendental functions with this construction. And an example which is not of this kind are polylogarithms. So these are also G functions. And here, for example, if you want to estimate the growth of the coefficients, so for the first n coefficients, you need to multiply. A common denominator will be the least common multiple of 1, 2, 3 up to n. And you can use, for example, that this is smaller than or equal to 3 to the n, okay, which is a weak form of the prime number theorem. Okay, so another example, and this is called a non-trivial example in Siegel's paper. So it's given by hypergeometric series. So there are two ways to think about them. One is by this explicit formula that I'm going to explain in a moment. But from the point of view of linear recurrences, these are kind of the easiest ones. So it's just length 1. It means that if you do the quotient of two successive coefficients, then this is a rational function of n. Okay, and out of this you get a differential equation. But if you want to explicitly write down what this means, you give yourself an integer p. Then parameters alpha 1, alpha p, rational, beta 1, beta p minus 1. So here it's important that they are not non-negative integers, non-positive integers. And then you consider this generating series, where the coefficient is a quotient of Pohammer symbols. So the Pohammer symbol is a generalization of the factorial. If you do Pohammer of 1, then you will find n factorial. And in general, you do x plus 1, and so on. And you see that here there is an n factorial. So you should secretly think that there are as many alphas as betas, and the last one is equal to 1. Okay, but somehow this is the classical notation. So this is a differential equation of order p. The radius of convergence is 1 because of this balanced number of alphas and betas. And the interesting part is the growth of the denominator. So this is what is proved in Siegel's paper. You need to study a bit the p-adic valuation of this thing, and this is done with the kind of formula that generalizes the p-adic valuation of n factorial. Okay, so let's do an example of hypergeometric series. So this is the most classical example. So it's f21, and the parameters are 1/2, 1/2, 1. In that case, you work out the coefficients that is given by this binomial coefficients up to the 16th. Here's the differential equation of all the two. But maybe the most interesting feature here is that you can also write this function as an integral. You get this elliptic integral. So here, if you take the z equals to 0, then you find the integral of dx divided by square root of x 1 minus x. This is not equal to 1. So is it equal to pi? So you need this factor 1/pi to match the constant term. And this integral representation realizes the hypergeometric series as a period function. So I will say a bit more later. And it's a period function. Well, the family, like the pencil of algebraic varieties, is given by this differential form. So you consider the family of elliptic curves defined by y squared equals to x times 1 minus x, 1 minus zx. So the Legendre's family. And then this function encodes the variation of periods here. So for example, the fact that it is a solution of a differential equation for the 2 reflects the fact that the cohomology here is of dimension 2. So once you consider one differential form, the derivative, second derivative, you have 3 of them. So there is necessarily a relation, and the relation is this one. And using this interpretation, you can also show that this function takes transcendental values at every non-zero algebraic point in the unit disk, okay? Because this get interpreted as periods of an elliptic curve divided by pi, and we know that those are transcendental numbers. Okay, so this is the kind of, ideally, this is the kind of information we would like to know for every G function. Okay, so what is the general situation? This is given by Picard-Fuchs differential operator. So I will consider a family of smooth projective varieties defined over the algebraic numbers. So S is some open inside A1. I'm going to assume that it contains 0 because the discussion is a bit simpler. And then associated to this family, there's a Gauss-Manning connection. So this is the vector bundle whose fiber is the algebraic de rank homology of the fibers. And a way to think about this connection analytically, so it can be constructed purely algebraically, but analytically, what you do is the following. So you place yourself on a analytic open small neighborhood of 0. So there you can take a section of this vector bundle. This is a family of the algebraic differential form indexed by Z. And you also have the local system given by singular homology of the fibers. So if you choose the open small enough is constant, so you can take a homology or a homology class in this constant local system. It will be the same in all fibers. So this does not depend on Z. And then you get a period function of the variable Z. You want to differentiate with respect to Z. And you can do this under the integral sign. And the Gauss-Manning connection is exactly what you get when you differentiate the differential form with respect to the variable Z. Okay? So this is the point of view of vector bundle with connection. But you can trivialize the vector bundle. You can choose a cyclic vector and then write your connection in terms of a differential operator, L. And one way to define Picard-Fuchs differential operators is to look at all the differential operators you get this way. They are maybe not irreducible, so you can factor them, and you can then combine all kind of factors, and the class you get is Picard-Fuchs differential operators. In more geometric terms, so these are pure objects, and then what you do is you consider all extensions given by factors of these Gauss-Manning connections. Okay. And then what is the relation to G functions is given by this theorem of André, which says that if you have such a differential operator and you consider a solution in power series with algebraic coefficients, then this solution is going to be a G function. Okay. And here, well, of course, you already have the differential equation. The convergence radius of convergence is also not an issue, and the statement is about the growth of the coefficients. And the key point is that once you have such a differential equation coming from geometry, you have some kind of Frobenius structure that gives you an isomorphism with a pullback by Frobenius. And then this makes that the series has to converge p-adically enough for the denominators to be controlled. Okay, so the main point. And in terms of our discussion, so period functions in general, as you saw here, do not have algebraic coefficients because the period function is the integral, so you have the pi. But what you get from the theorem is that they are linear combinations of G functions, and the coefficients are periods. Okay. This is the situation a bit simpler where 0 is not a singularity. And if you allow 0 to be a singular point of the family, then you need to put a bit of monodromy. But this monodromy, as we learned before, is the simplest possible. So it's quasi-unipotent. So you have some rational powers of Z and some integral powers of the logarithm corresponding to the Jordan logs. Okay. And because of this theorem, G functions have very interesting applications to algebraic geometry and number theory. So two themes I'm not going to talk about, but they maybe are the most interesting one. One is the study of Hodge loci, and I guess so some of the actors are here. I think we'll learn more about this in Christopher's talk. And another very recent, very exciting development is the proof of the irrationality of certain periods by Galegai, Dimitrov, Tang. Okay, so now second explanation of the name G. So I describe a natural source of G functions, so solutions of Picard-Fuchs differential operators. And then the Bombieri-Dwork conjecture is that this produces all G functions. Okay, so the slogan is usually all G functions come from geometry. And a way to give a precise meaning is that, well, every G function is a solution of a Picard-Fuchs differential operator. And one thing that this suggests, for example, is that if you look at special values of G functions, so you evaluate at a non-zero algebraic number inside the radius of convergence, this should be equal to the ring of periods. Actually, something funny happens, so you need to invert pi. 1 over pi is not expected to be a period, but you have a lot of formulas by Ramanujan of this kind, which show that 1 over pi is a special value of a G function, even a hypergeometric one. And ultimately, this is the reflection of the existence of some Hodge loci in a family. So it expresses, for example, this one expresses an algebraic relation between periods of elliptic curves with complex multiplication. And well, so that's the conjecture. This is what André himself calls the easiest part of the conjecture, the easy half of the conjecture. And one thing that was surprisingly not known is that all periods are special values of G functions. And this is something that we know how to prove with Peter-Jossen, for example. Okay, so this gives the half part of this expectation. Okay, let me give you some evidence for this conjecture. This is going to be quite short. So it is true for algebraic functions. So this corresponds to finite covariance. So families of algebraic varieties of dimension 0. It is also true for hypergeometric G functions. This is more interesting. It's related to cyclic covariance of projective space. And maybe for me, the most important evidence is that if you pick a non-zero G function, you consider the differential equation of minimal order that annihilates it. And there's this theorem of, well, it's a combination of results by these four that says that this shares with Picard-Fuchs differential operators. There's an important property that the singularities are regular and the monodrome is quasi-unipotent. And in particular, you can solve differential equations of rank 1 with this property. And so it's very easy. You just have a rational function. And this tells you things about the residues of this rational function. This tells you things about the order in both directions. And then you see that all G functions of differential order 1 are of this form. So they are all algebraic and they're of this very special shape. Okay, so the gammas are algebraic and these are rational. So these are the exponents. Okay, so we can say G functions of differential order 1 are understood. And then next is differential order 2. And there was this hope by Dwork that you could somehow produce all of them using hypergeometric functions, so the one for p equals to 1, and algebraic functions. Okay, so the statement, I'm going to show you some examples and explain what it means in practice, but the statement is that an irreducible operator of order 2 with a G function as solution, it's up to some equivalence relation, is a pullback of a hypergeometric differential equation of order 2. Okay, so typically this is what this means. So this is the place where I was happy to do a slide, so I could put this formula. So you consider, for example, this generating series. So Aperi famously proved that theta of 3 is irrational by constructing some very clever linear forms in 1 and theta of 3. But in the same paper, he also proves that theta of 2 is irrational without knowing that it is pi squared over 6. And one of the coefficients that show in the proof is this one. So you put it into a generating series, then you get a g function of order 2. It is a solution of this differential equation. And the kind of concrete implication of Dwork's hope is that you can write it as a hypergeometric series where you replace the variable by some rational function, and then you are also allowed to multiply by some algebraic function. Okay, so his question was if every g function of order 2 is of this form. And this was disproved. So first by Krammer in 95, and then there were further counterexamples, for example, by Martin, who is there, and that by Reiter. And maybe the message of the talk, so now I come to the main result, is that this hope was as wrong as it could be. So there's really nothing to say here. So the theorem is that there exist infinitely many non-equivalent g functions of geometric origin, solution of an equation of differential of order 2 that cannot be written as polynomials in hypergeometric series replacing algebraic functions times algebraic functions. Okay, so there are a few. Well, one thing that was left open in this work of Dwork's conjecture was if you could prove infinitely many, you could produce infinitely many counterexamples. And the other one is that in Dwork's case, this is the question is if a g function is equal to this thing when p is equal to 2. Okay, and here you are allowed to take all possible values of p and polynomials and do all kind of algebraic substitutions. Okay, so that's what I'd like to explain. So maybe some comments. So first comment is that this is very explicit. You can produce explicit examples as many as you want. So here's one, for example. You look at this differential equation where p is this polynomial, and this was written down in a paper by Surnovsky and Surnovsky. And any solution in power series with rational coefficients, for example, the one that starts like this, is an example of this theorem. So is this something that cannot be obtained in terms of hypergeometric series? So it is of order 2, which is the minimal possible, and it has 4 singularities, which is also the minimal number, because somehow everything with 3 singularities can be obtained from hypergeometric series. Okay, and the other comments are this was a question of Fischler and Rivoal. And then the motivation was that there was in Siegel's paper, so the main point of Siegel paper is E functions, which is more something like the exponential. It's the same definition, but you have an n factorial in the denominator. And then there was the question if everything was generated by hypergeometric series, and then a few years ago, I proved with Yichen that this is not the case. But for example, if the stars in differential equations have order 3, so it was very interesting to understand. Like, there were 2 interesting things. The methods do not apply at all, and then there is this gap between 3 and 2. And the other thing is that, as I said, there are infinitely many counterexamples to Dwork's conjecture, and actually this makes my presence here not completely unjustified, because to show that there are infinitely many would rely on some recent progress on unlikely intersections. But okay, the last slide is about this, but I'm not sure I will make it. So so this is the main relation to this session. Okay, so let me give you some sketch of the proof. So The beginning of the proof will, okay, we want to prove that some function is not of some particular form. And this is very hard. So we are going to work with the differential equations and actually with D modules on P1, but the only thing that matters is the generic fiber of the D module. So you could think of a module for this ring. And notice there's a subtle difference. Before there were brackets, so now there's parentheses. So this is a field. And we are going to define two categories of such modules that are called H, like hypergeometric, and G, like geometry. So G, what do? You consider all the modules given by Picard-Fuchs differential operators, so the cyclic ones. You take this ring and you quotient by the differential operator. And then you consider the Tanakian category generated by those with respect to usual tensor product. The Tanakian fundamental group is going to be the differential Galois group of the equation. And then inside, you have H, which is, well, what is the reason for H? So we want that all these functions are solutions of an object of H. Okay, so you need to find a differential equation for such a function. So what do? You start with a differential equation for the hypergeometric function. So these are given by this kind of differential operators. And then the substitution on an algebraic function and then multiplication by an algebraic function, this corresponds to this kind of operations. So you have a smooth curve C, have a finite ramified Galois covers P1 and P2, and then you can pull back your differential equation to C and then do the direct image. Okay, so you need to know that all these come from geometry, which we do, and then you consider inside G everything that is generated in a Tanakian sense by those. Okay. So as I said, every such function is a solution of an object of H. And now the goal is to construct an object of G of dimension 2, which is not inside H. And then this will produce the G function solution that is not a polynomial in hypergeometrics.
So you also allow direct sums?
Yeah, I allow direct sums. And I could allow extensions or not. You can have both versions. Okay, so that's the first step. So in principle, an object in a Tanakian category generated by something is quite, it's a bit a complicated thing. So you need to take several objects, do a tensor construction, take duals, direct factors, and so on. And the second step says that it's actually not necessary to do any of this. So this relies on differential Galois theory. Here is the computation of the differential Galois groups of hypergeometric equations by Boykers and Heckman. And the result is that you take an object of G of dimension 2. So the Tanakian group is inside GL2. We assume that it is big, so actually assume that it contains SL2. You can always twist by the determinant, that's not a big deal. And then the step 2 says that it is actually generated by a single construction of this kind. And H is not any hypergeometric differential operator, it's actually one of the two. Okay, so one where here P is equal to 2. Okay? So this makes things much more concrete. And then, so step 3 is where some invariance to detect objects of H appears. And it's going to be a trace field. So now I'm going to switch from differential equations to local systems. More convenient for this kind of invariance. So you consider the local system associated to a hypergeometric differential equation of rank 2. We assume it is irreducible. So this is a representation of the fundamental group of pi1 minus 3 points with values in GL2 of C. And the idea is to consider the field generated by all traces of all matrices given by rho of gamma on elements on the fundamental group. Okay. we need to do pullbacks and direct images by finite covers. And for this, we need something that is invariant under passing to finite index subgroups. And this is not true for the trace field. So it's better to work with something a bit smaller in principle, which is the adjoint trace field. So this will be a subfield. And we still take traces, but instead of this representation, we consider the adjoint representation on the Lie algebra of GH2 here. Okay. And then the claim is that this field is, this adjoint trace field is contained in a cyclotomic field. So in particular, it is abelian. And also it cannot be a real quadratic field Q square root of D for D bigger than or equal to 7. Okay. So this statement is a consequence of rigidity. So rigidity resolves by CATS for the hypergeometric differential equation. So this is roughly how it works. So as I said, the adjoint trace field is inside the trace field. And since the local system is irreducible, this is actually equal to the field of definition. So there are possible, there are many definitions for the field of definition, but the one I'm thinking about is if you have an automorphism of C, then you can compose your representation with the automorphism. So you get a new representation and a new local system. And then you want to know if this is sigma of H. You want to know if it is isomorphic to sigma of H. This gives a subgroup of the automorphism, and then you take the invariant field acting on C. Okay. So because of the assumption that these alphas and betas, they became A and B, they are rational numbers. So you can compute the local monodromies of the hypergeometric differential equation, and it will be roots of unity, and they are expressed as exponents 2 pi I. A1, for example, this will be one monodromy. So they are roots of unity. And this means that if you have something that fixes this root of unity, then this will fix all the local monodromies. But then this resolved by CATS on rigidity says exactly this, that if an automorphism fixes all the local monodromies of your local system, then it fixes globally the local system. Okay. And this is how you prove that this field is contained in a cyclotomic field. And the other part is a very amusing explicit calculation with cyclotomic fields. Okay, so once we are here, actually, what do we need to know to do? So we need to construct an object of dimension 2 of G with differential Galois group SL2, and for example, an adjoint trace field, which is not abelian. Okay, this will tell us that because of step 3, that this object cannot belong to H. And at this point, there are various ways to do this. So I'm going to explain one using Shimura curves. But this part here is here to produce more examples using Teichmüller curves. And this was already in the paper by Martin. But okay, let me stick to Shimura curves. So you can take a totally real number field F, a quaternion algebra over F, which is non-split, but it splits at some place at infinity and only one. And then you can choose an order in B. And if you make all these choices, then you have actually an orbifold curve, SH B0. And then you can take the complement of the finitely many orbifold points. And this gives you some open curve that carries a local system of rank 2. There are various ways to think about this. You can think in terms of the uniformization of the Shimura curve, or in terms of the modular interpretation as families of algebraic abelian varieties with an action of F. And okay, we want differential equations, so we are going to assume that this has genus 0. And then the statement is that this local system when you think of it as a vector bundle with connection, it is an object of G, so it's a vector bundle with connection coming from geometry. The differential Galois group is SL2, so here you think of the differential Galois group as the size-key closure of the monodromy, and the adjoint trace field is equal to F. Okay, so this is the key property for us. So then you just need to find some F totally real non-abelian for which there's some Shimura curve of genus 0. And there are tables by John Boyd where he kind of classifies all Shimura curves of genus 0. And you can go through the tables and then, for example, take F cubic. If F is cubic, there are two possibilities. So if it is Galois, the Galois group will be the cyclic group of all the three. And if it is not Galois, the group of the closure is going to be S3. And this, how do you distinguish these two cases? You need the discriminant to be a square or not. So if you have a F cubic with a discriminant which is not a square, for example, 148, then F is non-abelian, and then you get an example. Okay, and the explicit example I show at the very beginning is obtained by making some choice of a Shimura curve and computing explicitly this uniforming differential equation. Okay, so it seems that I will have time to explain this after all. Yeah, so this is a way to produce examples. So this is proof, sketch of proof of the theorem, except for the part that there are infinitely many examples. And for this part, what we do is, so we start with, okay, we are going to look at the moduli space M04. You have the universal family of curves of genus 0 with 4 punctures. And George and Daniel, they constructed a local system, and they constructed many local systems on C04 that come from geometry and more precisely from families of abelian varieties. And you can get a lot of control on the restrictions to every fiber. So for example, you can choose them in such a way that the monodromy group is SL2 in restriction to every fiber here. And in such a way that you have a control on the trace field or the adjoint trace field. So you can, for example, pick a root of unity of some order and then consider the totally real subfield of the cyclotomic field and then get a local system where all restrictions to fiber have this field as a trace field. Okay? The construction is very beautiful. It's given by middle convolution with some factor coming from an elliptic curve. And what we prove is that most fibers of this, in particular, infinitely many fibers of this local system here are not algebraic pullbacks of hypergeometric local systems. And then the argument is more or less the following. So assume okay, so you have some integral structure coming from the interpretation as families of abelian varieties. So you can consider a period map, and actually was more M04 will map to the period space associated to these kind of variations of hot structures. And then you argue that if there are infinitely many points which are of hypergeometric type, there will actually be infinitely many points which are isomorphic to the same pullback of a hypergeometric local system. And each of these points, so you pick one point where the fiber is hypergeometric, and every other point which the fiber is isomorphic to this one is going to be in the same Hecke orbit, generalized Hecke orbit of the first one. So if there are infinitely many, this means that you will have inside of the period domain, which is in this case a Shimura variety, you will have a curve which intersects like a curve whose Hecke translates intersect at many points, like infinitely many points. And a case of the André-Pink-Tsania conjecture that was proved recently by Richard and Javier says that this cannot be the case. So there are only finitely many such points. So we conclude that there are only finitely many fibers here that are of this type, algebraic pullback of hypergeometric. Okay, and I think that's all I wanted to say. Thank you.
So it seems like you didn't really use very much of a hypergeometric local system. So could you show, for example, if you replace H with the subcategory generated by all rigid local systems
we thought about this, and yeah, I'm not sure it really works. This was hidden, but there's something that uses very crucially the hypergeometric. It uses an explicit classification of the groups that appear. So yeah, if you assume that the thing is rigid and then the group is one of the classical groups, I guess the argument goes through. But what you need to do here is you consider all hypergeometric equations, and then they give you the list of monodromy groups, and then you want SL2 to be a quotient of this group. But the groups are essentially SLN and SP and O, and most of them are simple, so you cannot get them as a quotient. So if you have some information like this, I guess the argument goes through, yeah. Well, still you also need to know that rigid local systems are geometric, and you take those, yeah. I guess the conclusion is that already in differential order 2 and 4 singularities, there's a whole world there.
So this result related to the result of Colette and Simpson on these representations. There is this representations with question on them. Because it looks like the examples are exactly the same, like they come from the curves, or you have something coming from Schnorr, right?
Yeah, so yeah, I guess I don't know. I guess what this is saying is that even if you just consider geometry coming from families of abelian varieties, or there's already so much more than just hypergeometric things.
Yeah, but that's what they were saying. That either something is coming from curves, or it is coming from families of abelian varieties in the rank 2 case.
Yeah. So I'm not sure what's the question exactly. So
I just wanted to understand the relation is the things like they really describe systems that come from geometry, and they said how they look like.
Yeah, so I think if you use this result, okay, you can maybe in this category G, if you restrict to objects of dimension 2, then you have this control on the kind of geometry. And then what this is saying is that already inside of this very restricted geometry, the ones obtained by all kind of algebraic operations from hypergeometric ones are very special. Maybe that's what it is saying. I don't know. Because the construction we use by George and Daniel is very much related to this theorem.
What can you say about the diagonal grade of H and G functions and grades?
Of which function? This kind?
Just
objects at H, objects at G, is there any upper bound?
Yeah, so well, first you need to restrict to those which are globally bounded, and then well, I think we know for the hypergeometric. Well, there are many things we don't know about this question, as you know. Yeah, but then I think it becomes, when you start doing this kind of I don't know, this kind of substitutions, then it really becomes complicated. I'm not sure there is any non-trivial bound.